This lesson deals with Norton's theorem. You can find these notes in the course ebook in Chapter 3 starting on page 30. Let me state Norton's theorem. A two-terminal linear circuit with sources can be replaced by the short circuit current in parallel with the input resistance of the circuit with all the independent sources set equal to 0. Let me show you what that means with a drawing. We have a linear circuit. We can separate it into two boxes. I can replace this box with just one current source and one resistance in parallel. This is not the same as the circuit S, but it has the same effect at terminals A and B. The current source, I sub n, is found by taking this box and shorting its terminals and finding the current that flows from A to B. The resistance R sub n is taking this box and setting all the independent sources equal to 0 and find the resistance looking back in. Why is this true? Let's take the box, circuit S, take off the load that's there, the circuit L, and replace it with a voltage source that's capable of all possible voltages. And let's define a current I test in this direction and do the following. Let's solve for the current I test by using superposition. Let's set all the sources in box S equal to 0 and find I test due to V test. Call this current I test prime. It's I sub test due to the single source V test. Now the ratio of this current to V test is the resistance looking into the box. V test divided by minus I test prime is, say, R equivalent. I'm going to define that to be R sub n. Cross multiplying can then solve for I test prime, bringing that over here. What I'm left with then is V test divided by minus R sub n. Next, let's set V test equal to 0 and find the value of I test due to the sources in the box. Call this current I test double prime, and that's the current that's now flowing in this short circuit by setting this equal to 0. I would define that as the Norton current. It's sometimes called I sub short circuit. Now this is due to all the sources in this box, and applying superposition, we would just get a summation of terms that would give us this result. Put the results together. So the value of I test is I test prime plus I test double prime, and that's equal to our first result plus our second result. So given a box where we apply V test and a current I test comes out of it, can you make up a circuit that does this? Well, here we got a current, and it's equal to a summation of current. So I got two things in parallel. Let's put a current source I sub n pointing in this direction. The current I sub n is entering this node, and I've got I test leaving, and then I've got the current in here. The current in here is V test divided by R sub n. If I take the current that enters a node and define the current in this direction, that would equal the value of I test. But the current in this direction is this voltage divided by R sub n. So that's going to be a minus V test divided by R sub n. So I can make this equation by putting a current source in parallel with a resistance, whose value is R sub n. And this circuit has the same equations as this. I test is equal to I sub n plus this current, which is minus V test over R sub n. This is not the same as the original circuit, but it has the same effect at the terminals for all values of V test. So we say that it's equivalent. Let's do an example. Obtain the Norton equivalent circuit of this yellow box, which is to the left of the terminals A and B, and then use that to find the current in the 5 ohm resistor. By Norton's theorem, I'm going to take the box, take the load off of it, and replace it by a short circuit. And the current in that short circuit is my value of I sub n, and the current's going to flow from A to B. Now I have two sources. I could use superposition to find that current due to each source. Set the 12 volt equal to 0, that's a short circuit, and then I'll find the value of I sub n due to the first source. Two resistors in parallel, and the current in the 6 ohm resistor is the same as I sub n prime. I could use my current divider rule. I'll use the resistive current divider, which says that if I want the current in the 6 ohm resistor, I take the 4 ohm resistor and divide it by the 6 plus the 4 times the current that's coming into the parallel combination of 2 amps. That gives me 0.8 amps. Then we'll set the current source equal to 0 and put the voltage source back in and find the current due to the second source. Taking a current source equal to 0, it's an open circuit. Put my 12 volts back in, and now the current that flows in this direction would be equal to 12 volts divided by the total resistance in parallel with it. 6 plus 4 is in parallel with the 12 volt source. But I want the current in the other direction. So I'll take the negative of that. Minus 12 divided by 6 plus 4 is a minus 1.2 amps. And now I can add the two results together. The value of the Norton current in the short circuit with the load removed from nodes A to B is the first value of I sub n plus the second. 0.8 minus 1.2, that's equal to minus 0.4 or minus 400 milliamps in integer notation. Next, we need to find the Norton resistance. We're going to set the voltage source equal to 0 and the current source equal to 0 and look in the terminals AB. And all you see is 6 ohms in series with 4 ohms, and that's 10 ohms. So we can put the results together. We have a Norton current pointing towards terminal A, away from B, but its value is a minus 400 milliamps. And in parallel with that is a 10 ohm resistor. Now some engineers don't like negative signs, so they just get rid of this sign and just flip this around. And that becomes then the opposite sign of our current. So it'll be 400 milliamps in this direction. Both mean the same thing. Now let's take this result and put the load back on and find the value of I sub x. I've got two sources, so I'll set this source equal to 0 and find the current due to this source. If the current was in this direction, I would have a current divider with two resistors in parallel. If I want the current in the 5 ohm resistor, using the resistive current divider, I would take the other resistor over the sum of the two. 10 over 10 plus 5 times the current in this direction, which is a minus 400 milliamps. I'm going to add to that the current due to the second source, set this equal to 0 by being an open circuit. And now again, I could use my current divider rule that the current in this resistor is going to be the other resistor, 10 over the sum of the two, times the 4 amps. We've got 10 over 15, common, and then I've got 4 minus 0.4, which is 3.6, and that's equal to 2.4 amps. And this is Norton's theorem, an example illustrating it.